retract and deformation. Retract. Okay, so let's draw a picture first. It's always easier to see things via picture. Let's say this is some topological space, a disk, let's say. Now, this disk, let's say, it has a hole inside it, like this. And this is the annular region. We call it, let's say, the annular region. Now, what one can do is that one can obtain a loop by a continuous deformation of this boundary. Let's call this boundary as A. One can continuously deform it, shrunk the space like this. Or what one can do is that one can continuously deform it and make a loop like this, or another loop like this. Okay, so this is a retraction. So mathematically, retract. Let's say you have some topological space X. If you define a map that takes you from this topological space to a subspace of X. Okay, because see, I'm deforming this into a subspace. That is something inside the space, intuitively speaking. So if let's call this blue line as R. So if I have a continuous map F such that it maps this X to R, the subspace of it, such that if some bar R is equals to ID of R, this actually means that all the points in R is fixed. That's what it means. So if I have a map like this, then this map is called a retract. And this is called a retract. So what does it mean? Let's try to see it again with the picture. So at first I can draw a disk like this with a hole inside it, and then on the disk I can specify this region that is denoted by the blue circle, right? So when I shrink A, let's say the boundary over here, I shrink A, the points in R stay fixed, and I can continuously shrink that with the help of some function that takes every point in A, every point, let's say these points, and maps them to R. This is a retract. Now, what is a deformation retract? A deformation retract, so from this definition, in summary, you can say retract or retracting is the work of a function. Work of a continuous function. So it's taking data from some domain and it's just mapping those data to another region, right? Now we talk about the deformation retract. Deformation retract. In short, the deformation retract is nothing, it's just a continuous family of continuous deformations. That means This is actually a homotopy. That's what we mean by a continuous family of continuous deformations. So if I have to give you the mathematical definition, it would look like this. Let R be a subspace of X if there exists a continuous, let me just write CM, that means a continuous map, H such that it takes data from this X cross I thing. You can think of it as a square where this is X, this is I, and so on, but let's not do that right now, and maps it to X again such that my H of X comma 0 is equals to X, H of X comma T is equals to X. This means the point is staying fixed, and here you have H of X comma 1 that belongs to R for any small x belongs to capital X, and this condition means for any x belongs to R and t belongs to I. Again, you can think of I as 0 to 1. That's what the standard thing that we're dealing with. So this is a homotopy, and this deformation retract is nothing but a continuous family of continuous deformations. So if you have two, let's say, again consider the paths, you can continuously deform one path to another, let's say A and B. You can continuously deform it, right? But now there is not only continuous deformation, but there is actually a family of continuous deformations. Okay, so if the space is like this whole thing will deform again and again, and you can ultimately move from A to B with this continuous set of continuous deformations. It's a bit hard to visualize, but mathematically it makes more sense. So this is a deformation retract, and that's the essential difference between deformation retract and just ordinary retract, where the retract itself is just a function or a mapping which is also continuous. The deformation retract is a continuous set, continuous family of continuous deformations. And let's say you have a space like this with two holes inside it, and if you have, let's say this is your R and this is X, then this R can be, it's a retract, but not a deformation retract. Because you can think of some F that will take data from here and map this to R, and the hole over here doesn't affect it. But if you try to have a continuous family of continuous deformations, this hole would be a problem. This hole wouldn't let you do that. So that's why this R is a retract, but not a deformation retract. This idea is only for knowing, for your knowing purposes. And now that we're done with it, we can finally try to compute some fundamental groups.